This is Andrea Hendricks. The objective of this lesson is to show you how to graph a rational function that has a slant asymptote. These occur when the degree of the numerator is exactly one more than the degree of the denominator. And we're going to have to use long division to determine what that slant asymptote is. So let me just kind of review things a moment. When we say slant asymptote, we're really talking about a line that is not horizontal. So the form of the line is going to be y is equal to mx plus b. So that will be the equation of the asymptote, and we're going to follow a similar process to graph it like we've done before. We're going to have to find the vertical asymptote, the slant asymptote by long division, find the zeros or the x-intercept, the y-intercept, possibly some additional points, and then we'll graph it and find the domain and range. So let me illustrate this with the example of f of x is equal to x squared over x minus 1. So to find the vertical asymptote, we know that we're going to set the denominator equal to 0 and solve. So in this case we get x is equal to 1. We know it's going to be a vertical asymptote because the factor x minus 1 is not common with anything in the numerator. Now to find our slant asymptote, what we've got to do is divide x squared by x minus 1. Now you might recall we need to put in some placeholders for the other terms. So if we say x goes into x squared, we will get what? X, right? X times x is x squared. X times negative 1 is a minus 1x. Now we need to change the signs because we're subtracting. So combining those gives us x, what? Plus 0. Now we can say x goes into x one time. 1 times x is x, and 1 times negative 1 is minus 1. So now we change our signs and find that we have a remainder of 1. So remember we would write that as plus 1 over our divisor, which was x minus 1. Well, this is the interesting thing here, because now what we're saying is this, that x squared over x minus 1 is equivalent to x plus 1 over x minus 1. Well, that tells us that the behavior long term, that is as x goes to infinity, if we take x to infinity, this 1 over x minus 1 is approaching 0. Remember that if we have a constant divided by a number that gets larger and larger and larger, that's getting close to 0. So as we go to infinity, this is approaching 0, which means that this graph at its ends is really equivalent to x plus 1. So that's where we get that asymptote from. So our slant asymptote is y is equal to x plus 1. Now, we'll put all those pieces together in just a moment. Let's finish this. How do we find the zeros of the graph? Well, right, we have to set the numerator equal to 0. X squared is equal to 0 at 0. The y-intercept is plugging in 0 for x, so we would get 0 squared over 0 minus 1, which is 0 over negative 1, or 0. So let's plot what we found thus far, and then we'll look at finding additional points as we need them. So we have a vertical asymptote at x equals 1. Now, we have a slant asymptote at y is equal to x plus 1. So let's recall this. To graph a line, we can start with the y-intercept, and the slope is 1. So we'd have a y-intercept of 1, and we have to go up 1 over 1, right? So we get this line. Now it's really not part of the graph, but let me try to put it in here with the dotted line. And I want to be very careful because it's got to go through those particular points, because I need to figure out if other points are going to lie above or below. Let me see if I can move this over to where I need it to go. Yep, kind of. Oops. Okay, yes, I think that, well, let me move this piece down here over here just a little bit. Okay, I think that looks to be pretty good. So this is our slant asymptote, and the reason why that's important to be precise is when you plot these additional points you need to know if you're going to be above that line or below that line, so it's really important. And if you were graphing this by hand, you would probably take the time to do the rise over run and use a ruler and get that very precise. Now we know that we have a 0 at x equals 0. I'm going to put that in red. Okay, and do we know any other points from the information that we've been given? No. So let's try to now find some additional points. So we need some points to the right of our vertical asymptote. So let's plug in, let's say 2. If we plug in f of 2, we would get 2 squared over 2 minus 1, which is 4 over 1, or 4. So we know we have the point 2, 4. Okay. And maybe we want to plot something now to the left of the vertical asymptote, but we already know we have 0 there, so let's even go further than that. Plugging in maybe -1, f of -1 would be -1 squared over what? -1 minus 1, which is +1 over -2, which is a -1/2. So at -1, our graph is at -1/2. If you want to plot something to the right of 0 but to the left of 1, we can plug in a 1/2. So we would have 1/2 squared over 1/2 minus 1. So 1/2 squared is 1/4. 1/2 minus 1 is a -1/2. So we can multiply by the reciprocal to get 1/4 times -2 over 1, which is a -1/2. So what was that? When we plugged in 1/2, we got a -1/2 there. Okay, so this tells us that our graph is going to look like this. This is going to be an interesting shape to you. It's approaching that slant asymptote, but then it also is going to be approaching, that should be a curve there, this vertical asymptote. And that's hard to do on this graphing tablet, so I hope you apologize. I apologize, I hope you'll forgive me. I will show you on the graphing calculator what that will look like as well. And if we want some more points over here, we can get that. We know that we're going to never cross this vertical asymptote or the horizontal or the slant asymptote rather, so we're going to have a shape that looks like this. Okay. Now, what about the domain and range? The domain of our graph, the only value that we're excluding is the 1. So the domain is from -infinity to 1, union 1 to infinity. Now I'll tell you, the range here is going to be a little bit more involved, because what we've got to figure out is, are these points that we plotted the highest and the lowest point of those particular pieces of the graph? So just from what we've looked at here, we could probably guesstimate that our range is, for this bottom piece, -infinity up to 0. And we're including 0 there because we have a point on the graph. And then it picks back up at what this point was 4 and goes on up to infinity. But we can't really be sure unless we put that on the graphing calculator and find out the maximum and minimum. So let me show you the graphing calculator for this particular graph. Okay, so I've pulled up the graphing calculator and I've entered my function. And here is the graph of my function. I've again done it in dot mode. If you want to do zoom and z-decimal, the problem with z-decimal here is I'm off the screen because what's my value at? 4. You can change the window if you want. If you change the window in z-decimal, you just need to be multiples of these numbers that they have here. So my x, or y max rather, could be, instead of 3.1, I could be 6.2, and it doesn't change the niceness of the window. So here we see this graph. The thing that we really are paying attention to right now is this. Do we have a maximum in this particular piece of the graph of y equals 0? Do we have a minimum of 4? So if you wanted to confirm that with your graph, remember you have to do second and trace. We can choose maximum because we're going to look at the maximum of that lower piece. Then we have to enter a left bound, and then we have to enter a right bound, so we've got to go to the left and right side of that point, and then guess we go between the marks. And okay, when it does this, 9.66 times e to the negative 7, that really means times 10 to the negative 7, and the y value is times 10 to the negative 13. If you recall, that means there are 12 zeros in front of this 9.3, so that really is another way of saying 0. So we are right in the 0 for our top part of that bottom piece. Now we also need to find the minimum of the other piece, so if we go to second trace 3, we need to move right to that other graph. Okay, so you can see we're coming in on this other graph. We put in a left bound and a right bound, and then go between the marks and press enter. So look, yeah, we're at 2, 4, so 4 is our minimum point for that particular y value on that graph. So we have our range done correctly. Now let me take one moment now to do just one more example of this because it's kind of new, so I want to make sure that you're comfortable with it. So here again we have an example of x cubed plus 27 over 2x squared minus 8. So we have the case where the degree of the numerator is exactly 1 more than the degree of the denominator, which tells us we have a slant asymptote. So we begin by finding the vertical asymptotes, which is where 2x squared minus 8 is equal to 0. So we can solve with the square root property to get 2x squared is equal to 8. Dividing by 2 gives us x squared is 4. So notice now we have a plus or minus 2 for our vertical asymptotes. Now to find our slant asymptote, we've got to divide 2x squared minus 8 into x cubed plus 27. So we can put in some placeholders here. So we say 2x squared into x cubed, which is ugly. If you need to do that, it might be easiest to think of it as x cubed divided by 2x squared. Well, that leaves just what? 1/2 x, right? Because the x cubed divided by x squared, we subtract exponents to get just an x. So that's a 1/2 x. So 1/2 x times 2x squared is going to be a 1x cubed. 1/2 x times negative 8 is what? A negative 4x. So now we change our signs, and so we would get a 4x plus 27. But now look, 2x squared does not go into 4x because our degree is less than what we're dividing by. So we can stop and put this as a remainder over 2x squared minus 8. So here again we can say that x cubed plus 27 divided by 2x squared minus 8 is equivalent to 1/2 x plus 4x plus 27 over 2x squared minus 8. Well, remember what we're looking for is the slant asymptote. What happens long term? Well, as x goes to 0, or I'm sorry, as x goes to infinity, this expression is going to 0 because the degree of the denominator is more than the degree of the numerator. So that whole thing is going to 0 as x goes to infinity. So the equation of our slant asymptote is y is equal to 1/2 x. Now, what are the zeros of our function? The zeros are where the numerator, x cubed plus 27, is equal to 0. Well, that factors to be x plus 3 times x squared minus 3x plus 9, if you remember that sum of cubes pattern. So we get 1, 0 to be x is equal to negative 3. If we solve this other piece, we were going to get two complex solutions. So our only real 0 is at negative 3. Now what about our y-intercept if we plug in 0 into the function? Well, we would have 0 cubed, which is 0 plus 27, which is 27 divided by 0 minus 8, which is negative 8. So we get negative 27 over 8, or if you want, you can write that as a decimal of negative 3.375. So let's place some important information that we found on our graph and see how we can finish it off. So if we want to graph our vertical asymptotes at negative 2 and 2, and now we have a slant asymptote at 1/2 x. So remember that has a y-intercept of 0, we rise by 1, run by 2. So just to kind of think about where that would be, we rise 1, run by 2, rise 1, run by 2. Okay, so let me see if I can get my slanted line on here where I need to have it. And of course I'm not. Kind of close there. Slide that down there just a bit. I think that's pretty good. Okay. So now what we want to do is plot our 0, which we know is at negative 3. And our y-intercept f of 0 is at negative 3.375. Okay, which is somewhere right there. Now, if you wanted to get some additional points to know what the shape of the graph looks like, you could certainly do that. But here we know what's going to happen to the left of this negative 2. Our graph is going to approach this slanted asymptote and also approach the vertical asymptote. So we're going to look like this over here. We don't really know what's happening between the negative 2 and 2, so we should find some additional points there. We also don't know what's happening to the right of the 2. So let's plug in, let's say, what about f of negative 1? So we would have negative 1 cubed plus 27 over 2 times negative 1 squared minus 8. Now you could use your calculator to do all this. Negative 1 cubed is negative 1 plus 27 is 26. Over what? 2 minus 8 would be a negative 6. So negative 26 over 6, or negative 13 thirds, I think is negative 4 1/3, negative 4.33. So we have at negative 1 a negative 4.33 right here. Okay, we also need to know what's happening on the right side of this y-intercept. So if we plug in positive 1, what is happening? We plug in positive 1. We're going to have 1 cubed plus 27, which would be 28, over what? A negative 6. So 28 over negative 6 is going to be a negative 14 thirds. Okay? So that's going to be what? A negative 3 and 2/3? No, I can't even think. Negative 4 and 2/3. Okay, so that's going to be a negative 4.667. Okay, so here we think the graph is going to look something like this. Okay. And what about to the right of 2? Let's plug in 3. If we plug in 3, we're going to find 3 cubed is 27 plus 27, which is 54, over what? 3 squared is 9, and 9 times 2 is 18, minus 8, which would be 10. So that's going to be a 5.4. So at 3 we have a 5.4. 1, 2, 3, 4, 5.4. So that one point is sufficient to tell us the graph is going to look something like this. Okay. So now we can find the domain and range. The domain of this function just excludes our vertical asymptote. So we're from negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Now what about the range? Let's think about that. This line, what's the domain of this line? Negative infinity to infinity. So as we go to the left and right of the graph, we're approaching that all the way down. So this piece to the left is actually approaching negative infinity. The piece to the right is approaching positive infinity. That's also true with our asymptotes. So when all is said and done, we will actually have covered all real numbers from negative infinity to infinity. Okay. Now we can confirm all of this on our graphing calculator. Let's look at that. If we enter this graph, so we have x cubed plus 27 close parentheses divided by, in parentheses, 2x squared minus 8 and graph. Now why am I not seeing my middle piece? It's because I was in the z decimal mode. If I go to my window and I extend my y min to a negative 6.2, or I can put it in the standard viewing window, I see the graph that I need. Okay, and you can confirm if you press second and graph some of those key points that we found in our graph, and this would probably be the easier way to do it whenever you're actually trying to find points, is just to use them from the graphing table. Okay, so if you have any questions on how to work with these slant asymptotes, you know what to do. Thanks.